The focus of this lesson is on finding the horizontal or oblique asymptotes of a rational function. So we're going to start off with the function f of x equals x squared minus 4 divided by x squared plus 5x plus 6. In order to determine the horizontal asymptote, what we need to do first is we look at both the numerator and the denominator and look for the highest power of x that we see. And we can see that the highest power of x that we see is degree 2. So the way we would handle that is we would take our function and we would take every single term and we would divide it by that highest power of x. So in this case, x squared. So x squared divided by x squared minus 4 divided by x squared, and then take the denominator, the x squared divided by x squared, the positive 5x divided by x squared, and the positive 6 divided by x squared. So again, you can see we've divided the numerator and the denominator by that highest term, x squared. And so then what we do is we basically have a bunch of little fractions that we could cancel down or reduce down to lowest terms. So we know that if we have a numerator and denominator that are identical, they divide out to be 1. But if we have a case where we go to do division and we're left with an x in the denominator, well, I'll just kind of show that for now. So we're just kind of leave this. We could see this. This is as simple as it gets. And then x squared divided by x squared is 1, plus 5x divided by x squared is just 5 over x. And then 6 divided by x squared doesn't reduce any further. So we can see that after canceling out the common factors that this is what we're left with. Well, anytime there's an x in the denominator, since we are talking about a horizontal asymptote, we're thinking about the x going to either positive or negative infinity. And so it's either a really big number or a really small negative number. And so whenever you take a constant and you divide it by something really big or really small, it goes down to 0. And so all these terms that have an x in the denominator go to 0. So we're going to actually replace those terms with 0. And that's always the case. So we can see that we're left with just 1 minus 0, 1 plus 0 plus 0. And so the result is just 1 over 1, which is 1. So the horizontal asymptote is y equals 1. And that's a horizontal line that goes through 1. We're going to go ahead and take a look at a second example. So we're going to look at the function f of x equals x squared plus 2x plus 3 divided by x cubed plus 2. So again, we're going to look at both the numerator and denominator and look for the highest power of x. And so we can see that the highest power of x is x to the third. So we're going to take every term and divide it by x to the third. So x squared divided by x to the third, 2x divided by x to the third, 3 divided by x to the third, and then do the same thing for the denominator. We got x cubed divided by x to the third, and we got 2 divided by x to the third. And then what we're going to do is we're going to reduce all of those fractions down. So in the first fraction we're left with 1 over x plus 2 over x to the second plus 3 over x to the third. And then in the denominator, we're left with x cubed over x cubed is 1 plus 2 over x to the third. And so you can see that any term that has an x left in the denominator should go to 0. And then obviously this constant 1 stays. And so we're left with 0 divided by 1, which is 0. So we were left with the line y equals 0. That's our horizontal asymptote for this function. We're going to go ahead and take a look at one final example. We're going to look at the function f of x equals x squared plus 1 divided by x. And again, we're going to look for the highest power of x, which is x squared, and we're going to divide every term by that. So we get x squared divided by x squared, 1 divided by x squared, and from our denominator, x divided by x squared. And so again, we reduce each fraction. X squared over x squared is 1, plus 1 over x squared is just 1 over x squared. And x over x squared, the x cancel out and leave you 1 over x. And so wherever there's an x remaining, those terms are going to go to 0. And so we're left with 1 plus 0 over 0, which is just 1 divided by 0, which we know to be undefined. And so if it's undefined, that means there's not a value. So we were trying to find a horizontal asymptote, so there are none. So we'd say there's none. So when you're trying to find horizontal asymptotes, there's none. So in this case, if we don't have a horizontal asymptote, we move on to finding the oblique asymptote. And the way you go about finding the oblique asymptote is by doing long division on your function. So x squared plus 1 divided by x. And so I'm going to go ahead and set up my division, and if I'm missing any powers of x, I'm going to put a placeholder or 0 placeholder in, and so x is going to divide into x squared plus 0x plus 1. So x goes into x squared x times, that's our division step, then we multiply x times x, and then we go to subtract, and we get 0x squared, or we could just say 0, and then we go to bring down our next term. So basically we're taking x and dividing it into 0. Well, x doesn't go into 0, it goes in 0 times. And so 0 times x is just 0x, or just 0. And again, I'm just writing in the x's just to kind of keep our placeholders lined up. I don't need to. I could just write 0 here. And then I go to bring down, and I'm trying to divide x into 1, and it does not divide into that. So that is our remainder. And so normally you would take your remainder and you would divide it by your divisor, which is x in this case. And so we're left with the quotient x plus 0, and with the remainder 1 over x. Now, since we are talking about x going out to positive or negative infinity, because that's what happens when you're talking horizontal or oblique asymptotes, that means this fraction 1 over x, this remainder piece, and this will be the case every time, goes down to 0, because 1 divided by something really big goes to 0. And so you basically, in a sense, disregard the remainder piece. And so at the end of the day, we would say that our oblique asymptote is y equals, you don't need to write the 0, so it would just be y equals x. And that completes this third example on horizontal or oblique asymptotes. What I want you to notice in these 3 examples, I was intentional on the examples I actually picked. I picked an example where the leading term's power was the same, the leading term's power had a higher power in the denominator, and the leading term's power had a higher power in the numerator. So those are your 3 cases of how the powers can play out as far as being equal or higher in the numerator or denominator. And so that's what these 3 examples represent here in the red, green, and purple. So in the first example, notice that the powers were the same. In that case, if you think about the coefficient on those leading terms, so I'm just going to kind of go here and write it in. The leading coefficient's 1 and the leading coefficient's 1. Well, the horizontal asymptote will always be the leading coefficient divided by the leading coefficient. So 1 divided by 1 is 1. And so that's why our horizontal asymptote is what it is. So I don't necessarily want you to memorize that, but it's something to observe. So for example, if these were different values, like say a 2 and a 3, then it would be y equals 2 over 3, so 2/3. So in this next example, or the second example, the higher power was in the denominator. Well, when that happens, you're always going to have a horizontal asymptote of y equals 0. And then in the third example, the higher power was in the numerator. When that happens, there will always be no horizontal asymptote. In fact, the way I kind of think of it is if I can do division, there's not going to be a horizontal asymptote. Instead, it's going to be oblique, and I need to go ahead and perform the division to find that oblique asymptote. So hopefully that makes sense. But those are your three cases, and again, you could in a sense memorize that. But if nothing else, go ahead and go through the procedure I showed you for finding a horizontal asymptote. And then if you do not find one, you need to go ahead and determine the oblique asymptote instead.